and welcome to the second video in the series for Calculus 2 over Thanksgiving break, that is specifically Calculus of Integrals. So, this time we are talking about the integrals involving parametric curves. Specifically, we are going to be talking about using integrals to calculate the area underneath a parametric curve, as well as later we will talk about using integrals to calculate the arc length of a parametric curve. So, in beginning, from earlier, to calculate the area under a curve, we use an integral involving y and dx. The issue with this is we are now talking about inputting values of t. So, we can do a similar thing to what we did with derivatives of parametric functions, and we can write dx as dx over dt times dt. Now, at this point, we can shorten the formula and note that since from above we have x is equal to x of t and y is equal to y of t, dx dt is going to become x prime of t, and y is the same thing as y of t. And this gives us our final answer for the area underneath a curve defined parametrically, assuming the curve does not intersect with itself. Now, let's apply this idea to calculate the area under the curve defined by x is equal to 3 cosine of t plus cosine of 3t, and y is equal to 3 sine of t minus sine of 3t over the interval 0 to pi. So, to do this, we will use our formula, and then in the process we will have to take a derivative of the function for x. So for the formula, we note that a is 0 and b is pi for the limits, and then we're going to have y of t times x prime of t dt. From here, we note that the derivative of 3 cosine of t is negative 3 sine of t, and the derivative of cosine 3t is negative 3 sine 3t. So, combining this derivative of x, which is shown right here as x prime, along with y of t, we get this integral for the area under the curve. This could be calculated by hand, however the calculation is long and a little bit tricky with the need to multiply out and deal with things like sine of 3t. So instead, for these problems, we may choose to use a computer integrating program, and doing so gives us that this integral is approximately negative 9.424. You may wonder as to how the area under the curve is negative, especially when sine, the y values, are positive through the entire interval 0 to pi. The reason comes in the direction this curve is traced. Sketching this curve shows that the curve starts out at 4, 0 for time is equal to 0, and then moves to the left, reaching a high point of 2 at time is pi over 2, and finishing at negative 4 as time is equal to pi. Because this goes from because this goes from right to left, meaning x gets smaller as time increases, that ends up creating a negative integral, as was the case for our regular integrals. When we switch the limits, it turned the integral into the opposite value. So that is the reason that this integral ends up being negative for area under the curve, despite the fact the entire curve is above the x-axis. Now, let's talk about arc length of a parametric curve. So, for this example, we have a curve that resembles a set of stairs going from x of t1, y of t1, to x of t2, y of t2, and we want to measure the length of this curve. The simplest item to measure length of is a line. And so we could split this curve up into lines between points. So if we take 4 points, they can be whatever we want them to be, and we connect them with lines, we get a path with diagonal lines. Now, again, on a coordinate axis, measuring diagonal lines can still not be done immediately, as our points are given in horizontal and vertical directions. So from here, we will need to sketch right triangles showing the change in x and the change in y between each of these points to calculate the length of each of the line segments. So looking at the first one, a right triangle, we consider this first part delta x1, and the vertical part is delta y1. Specifically, the length of this first one, which we will call L1, can be calculated using the Pythagorean theorem. So, L1 is equal to the square root delta x1 squared plus delta y1 squared. We want to use the variable t, so at this point, we multiply the right side by delta t over delta t, and then move the denominator into the square root by rewriting delta t as the square root of delta t squared. The result comes out to L1 is equal to the square root delta x1 over delta t squared plus delta y1 over delta t squared times delta t. Now this results for finite delta x and delta y. If we are looking for an integral, we want to make delta x, delta y, and delta t infinitely small. Also, we would be doing a sum to find the length of this curve, so we would be taking the sum of each of these square roots. For finding the total arc length, we would be using an integral instead of a sum, and that then results in the formula. The arc length is equal to the integral from t1 to t2 of dx dt squared dy dt squared. As a reminder, delta x1 and delta y1 become dx and dy as the interval gets infinitely small, and delta t turns into dt as the interval gets infinitely small. What this means is that to calculate the arc length of a function, we will take the derivative of its x component with respect to t, square it, add the derivative of its y component with respect to t, square it, and then square root them and integrate this result from t1 to t2. Most of these integrals will have to be done by computer because exact results when we are talking about addition under a square root for antiderivatives are not often occurring. So, with that being said, let's use this idea to calculate an arc length. So, let's calculate the arc length of the curve given by x is equal to t cubed, y is equal to 7t to the fourth, between 2 and 5 for t. Again, this starts out with our formula. So, for this function, dx dt will be the derivative of the x component, which will be 3t squared. As a reminder, we then square this derivative for the actual integral formula. We next take the derivative of the y component, which is 28t cubed. This is also then squared as we set up the full integral. From here, it is best to do this integral in computer, as doing this analytically is not easy, and possibly, I'm not sure for this case, it might be impossible to do this analytically. Either way, we can use a computer for this derivative and we end up getting 4,264.687. So that is calculated arc length. For parametric functions, that sums up all of the calculus that we will be doing with them. If you have any questions, I invite you to email me or stop by my office when we get back from break. Thank you again for watching. I hope you have a happy Thanksgiving if this is before Thanksgiving. If this is later on, I hope you enjoy the remainder of your break. Thank you. Bye.